Welcome to MSB lecture series on the chemistry of main group elements. MSB stands for MS Balakrishna. In my last lecture, while discussing valence bond theory, I mentioned about the geometry and shape of water molecule. Now let me continue from where I had stopped. Let us look into the fundamental molecule that was used by Linus Pauling to explain the hybridization concept, that is methane. I was supposed to begin with methane. Since I wanted to go in the sequence, I started with first beryllium dichloride because it has sp hybridization, and then I discussed about sp2, and also I discussed about sp3 hybridization in case of water molecule where we have two bonded pair and two lone pairs. Now let us consider methane, and in methane we have carbon as well as hydrogen. Carbon electronic configuration is 1s2, 2s2, 2p2. So, prior to the hybridization, this one of the s electron is promoted to the p orbital to have s1 p3 electronic configuration. Now, these 4 orbitals will combine together to form 4 sp3 hybrid orbitals having 1 electron each, and now they are disposed tetrahedrally, and each sp3 with 1 electron would combine with 1s1 orbital of 4 hydrogen atoms to form 4 CH bonds. You can see here. So, sp3 hybridized 4 orbitals are disposed in this fashion, and now they combine with 4 hydrogen atoms to form 4 CH bonds, and this is a highly symmetric tetrahedral molecule having the bond angles of 109.5. And I have also listed many other examples. All tetravalent carbon compounds, whether it is tetrabromo, methane, tetrafluoromethane, all show sp3 hybridization. Besides this one, molecules having one lone pair such as ammonia, PH3, H2O, SiO4, 4 minus, SO4, 2 minus, perchlorate in all central atoms possess this sp3 hybridization, and they have tetrahedral geometries. You can always make an attempt to write in the same way for the rest of the molecules I have shown in the slide. So, let us look into ethylene. In case of ethylene, it is slightly different. Here once the electron is promoted to one of the empty p orbital, now one of the p orbital is not utilized, only 2 p orbitals and 1 s orbital will combine together to form sp2 orbitals having 1 electron each, like this. Okay. So, these are at an angle of 120. So, that means 2 carbon atoms would position in this fashion. So, these three are sp2 hybrid orbitals having 1 electron each, and these terminal 2 here and 2 here 4 sp2 orbitals with 1 electron will combine with hydrogen atom in this fashion to make 4 covalent bonds. Now, we have this empty orbital, they are at orthogonal to this sp2 plane. So, they have 1 electron each. Now, these two will orient in this fashion. They orient in this fashion, to form a pi bond. That means they interact in this fashion to form pi bond. As a result, what happens in case of this one, we have a sigma bond and we have a pi bond. and here these two are covalent bonds. For example, in this ethylene molecule we have 1, 2, 3, 4, 5 covalent bonds are there and 1 pi bond is there. So, this is also covalent bond. So, 5 sigma bonds and 1 pi bond is there. You can see this one in this slide here. See, this is how sp2 are oriented, and now the terminal ones are combined with 4 hydrogen atoms, and now we have 2 p orbitals on each carbon having 1 electron. They combine together to form pi bond. So, this is how we can explain bonding in case of ethylene molecule using this hybridization concept or valence bond theory. Let us look into one more example, acetylene. Again in acetylene, carbon promotes one of the s electron to the p orbital, and we have a situation like this. So, now we have 4 orbitals having 1 electron each. So, in case of acetylene, carbon utilizes only one of the p orbital, preferably pz, and these two are combined together to form 2 sp orbital having 1 electron each. They are oriented in this fashion. So, they have 1 electron each here, 1 electron here. As usual, these one of the sp from each carbon will combine with hydrogen atom, and now we have 2 p orbitals on each one having 1 electron each, and now they are overlapping in this fashion. So, now what we have is, in case of acetylene, we have 1 sigma bond, another sigma bond, and 1 pi bond, another pi bond. So, that means in this one we have 1, 2, 3 sigma bonds and 2 pi bonds. So, you can explain bonding in acetylene. We have arranged 2 sp orbitals having 1 electron each and unutilized 2 p orbitals having 1 electron each, and they come close to each other to establish a bond. And now this is how you can explain the bonding. Now only I have shown sigma bond in this one, 3 sigma bonds I have shown. Now these 2 p orbitals and these 2 p orbital will interact together. Similarly, this 2 p orbital and this 2 p orbital will interact together to form 2 pi bonds having 2 electron each. Pi bond begins and you get acetylene molecule like this. So, this is how you can explain the presence of 3 bonds between 2 carbon atoms in acetylene. Let us look into higher hybridization. Let us consider the example of PCl5. PCl5 central atom is P, and from VSEPR theory we have predicted it to be having trigonal bipyramidal geometry. Here we had 10 pairs of electrons, so that was giving 5 steric number and all are bonded. So, when the steric number is 5, the geometry is trigonal bipyramidal. So, let us look into it from valence bond theory. So, let me write, of course, here we have to utilize d orbital, and in case of phosphorus the electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p3. So, here we have 3d orbital also, but that is empty. So, let me write in this fashion, empty orbital of high energy. This is 3d. Next we have 3p orbital having 1 electron each, and then we have 3s having 2 electrons. Okay. So, now basically this s orbital and this p orbital and one of the d orbital will combine together to form sp3 dehybridization 1, 2, 3, 4, 5. So, now 1, 2, 3, 4, 5 electrons are there. These 5 electrons will occupy 5 sp3 d hybrid orbitals, and these 5 sp3 hybrid orbitals are oriented in a trigonal bipyramidal fashion. Let me show you in that one in the next slide. So, this is how the structure looks like for PCl5. We all know. Let us see how these hybrid orbitals orient and combine with 3p orbital of chlorine. So, this is how these 5 sp3d hybrid orbitals are oriented, and now they combine with 3p orbitals to form PCl5. So, you can explain very conveniently the structure of PCl5 using hybridization concept. So, let us look into another example of group 16 element, that is sulfur, appearing at maximum ox state, that is SF6 sulfur hexafluoride. Okay, so, let me write again the electronic configuration of sulfur. 1s2, it is below oxygen, 2s2, 2p6, 3s2, 3p4. If we do not remember the electronic configuration, we should try to remember to which group it belongs, and then also we should remember what name it is given to the group, if a particular name exists for a particular group like pnictogen, chalcogen, in that fashion. So, we know that sulfur is below oxygen. So, its electronic configuration is same as that of oxygen. Once you know that one, you should be able to write the electronic configuration. This is 1s2, 2s2, 2p6, 3s2, 3p4. Now, again we have high energy d orbitals. Like this, we have 4 electrons here, and then we have 2 electrons. Now these 1, 2, 3, 4, 5, since we have 2 extra electrons, they can be promoted to 2d orbital. As a result, what happens? It utilizes 2 more orbitals to form 6, 1, 2, 3, 4, 5 and 6 hybrid orbitals composite of 1s and 3p and 2d. So, 1:3:2, and now each one has 1 electron each. So, there are 6 orbitals are there. They are disposed to the 6 corners of an octahedron. So, this is the structure of SF6, it is octahedral, and this is how 6 sp3d2 orbitals are disposed along z minus z, x minus x, y minus y axis, and now they combine with 6 2p orbitals of fluorine atoms to form this octahedral molecule. Of course, here we are utilizing d orbital and say that they have the sulfur undergoes sp3d2 hybridization. When we go to the molecular orbital, it essentially gives a different combination of atomic orbital and different structure altogether. Of course, the geometry is octahedral, but molecular orbital depicts its formation in a different way. I should tell you more about that one when we go to the group 16 chemistry, because SF6 as well as SiCl6 2-, they are called hypervalent molecules. Okay. So, I will elaborate about these things and also how we are utilizing the atomic orbitals to explain the bonding in SF6 as well as SiCl6 2- while discussing the chemistry in the respective groups. So, let me take a simple example before I proceed further. to make you familiar with valence bond theory, especially for polyatomic molecules. Let us take a simple example as acetone, and let us try to look into the bonding of each carbon atom and also oxygen atom and describe the structure of the entire acetone molecule using hybridization concept. So, now let me first write the structure of acetone. This is the structure of acetone. Here we have 4 atoms are there besides hydrogen, this carbon, this carbon, this carbon and then this oxygen. And from the structure I have written, you should be able to clearly see the kind of hybridization one can think of for each atom present here, and this carbon should be of sp3 in nature, and this carbon should be of sp3 in nature, and this carbon should be of sp2 in nature, and this oxygen should be of sp2 in nature. Okay. So, let us see how that happens. Now, without going into the electronic configuration, since you are all familiar with electronic configuration, what I will do is I will simply write the corresponding hybridization and the corresponding orbital, and I show their overlapping to describe the structure of this acetone molecule. So, here this one. So, this carbon has undergone sp3 hybridization having 4 sp3 orbitals with 1 electron each, and 3 sp3 orbitals will combine with hydrogen atoms, and then this one will combine with one of the sp2 and this will also combine with one of the sp2 and one sp2 is here. Okay. So, here this carbon has undergone sp2. So, it has 1 electron here in one of the p orbital, and then oxygen also undergone sp2 hybridization. So, that means that you may not be familiar. Let me write in case of oxygen how to explain sp2 hybridization. In case of oxygen, we have 2s2, 2p4, of course 1s2. And now, if this oxygen undergoes sp2, in that case what I should do is we have a situation like this. So, we have a situation 1 electron here, 1 electron here. So, it undergoes sp2 hybridization. When it forms 3 sp2, you should remember 2 of them have 2 electrons and 1 has 1 electron. So, that means here essentially oxygen, this 1 electron here, and these are lone pairs, 2 electrons are there, and we have 1 p with this electron here, and these two will combine together to form a pi bond. So, essentially in case of acetone, now I can write one CC bond, another CC bond, and 3 H bonds, CH bonds, and here 1 sigma bond and 1 pi bond, and oxygen and lone pairs. So, no matter how complicated the molecule looks like, if you start one at a time, we should be able to write and describe the structure of any such molecules. For example, you can take even bigger molecules and you can make an attempt to write in this fashion to make yourself familiar with this hybridization concept. So, let me introduce one more term that is often used in valence bond theory, that is Bendt's rule. What it says, more electronegative substituents prefer hybrid orbitals having less s character, that is more p character, and more electropositive substituents prefer orbitals having more s character, that is having less p character. That means, if you consider a homoleptic molecule such as methane, or tetrabromomethane, we have sp3 hybrid orbitals, all are equivalent, and each sp3 has 25% s character and 75% p character. But when we have heteroleptic molecules, for example dichloromethane, difluoromethane, and here we can identify two different type of peripheral atoms bound to carbon. One of them is more electronegative, another one is less electronegative or more electropositive. So, in that case Bend's rule comes very handy in explaining the bonding, especially the variation in their bond angle. So, how to again I define the Bend's rule with this information. So, more electronegative substituents prefer hybrid orbitals having less s character, and more electropositive substituents prefer orbitals having more s character. So, this is how you can explain Bend's rule. Then we can use this Bend's rule successfully to explain bonding in molecules such as methane or trifluoromethane or difluoromethane, etc. Let us take CH4. So, I have given here three examples. One is methane, other one is tetrafluoromethane, and the third one is difluoromethane. It can be difluoromethane, or even can also write dichloromethane. In all the four cases, we are using sp3 hybrid orbitals of carbon combining with either hydrogen or fluorine or chlorine corresponding orbitals to form these molecules. In case of methane and in case of tetrafluoromethane, no issues, all bonds are identical. As a result, still each sp3 has 25% s character and 75% p character. But that is not the case when we go here. So, here according to Bend's rule, two CF bonds utilizes sp3 orbitals having more p character, and these two CH bonds utilizes orbitals having less p character or more s character. That means, I can write in this fashion: two CF bonds utilizes sp3 plus x, okay, and 2 CH utilizes sp3 minus x. That means, here automatically you can see here in these cases p contribution is more, whereas in these two cases p contribution is less, or in other words s contribution is more here and s contribution is less here. So, what would happen on the overall bond angle if this anomaly exists? So, in case of sp3, imagine if the p character increases, you just imagine the combination of 3 p orbital in the absence of s, it would be 90 degree with respect to each other, because px, py, pz are orthogonal to each other, the angle between them is 90 degrees, and if s character decreases, as a result what happens, the angle will start decreasing, it will come close to the 90 degrees. On the other hand, if s character increases, okay, it will go from 90 to the maximum tetrahedral angle of 109.5. So, with this information we should be able to write and predict the variation in the bond angle just simply based on the electronegativity of the atoms that are making the bond with the carbon. So, in this case we can say clearly that the FCF bond angles are lower, smaller. That means, I can say FCF angles are smaller than H, C, H angles. In fact, this is more pronounced in case of pyramidal molecules of phosphorus, arsenic and antimony. For example, if you take BH3, SbH3 or AsH3 or the corresponding trichlorides, this Bent's rule is more pronounced. Again, we can explain there by looking into the difference in electronegativity of these atoms. And besides this, one can also use some other means to explain this one, that is simply looking into the electronegativity difference between the central atom and the peripheral atom. So, I hope it is clear here. So, here the sp3 in case of CF and CH are different. In case of CF, sp3 has more p character, in case of here sp3 has less p character. When the less p character is there, angles are close to the tetrahedral or greater than 90, or in case of fluorine where the p character is more, that is coming close to the 90 degrees. So, let us look into one example here. You can see that example given here, why XPX bond angles for the series of POX3 molecules. This is POX3 molecule. This is POX3 molecule where X equals bromine, X equals Cl, X equals fluorine. So, here angles are given X, P, X angles are given here, and in this case it is 104.1, 103.3 and 101.3. So, that means angles are decreasing when you go from bromine to fluorine. On the other hand, angle is increasing when you go from fluorine to chlorine to bromine. So, again here same analogy one can use, the electronegativity of the atoms are decreasing, okay. Electronegativity of halide ions are decreasing. As a result, what happens? The p character is increasing. As a result, when the p character is increasing, the angle will decrease. Angle will decrease. Of course, here all the angles are less than 100. Here the Bent's rule may not be very precise to explain, but we can explain using the electronegativity difference between P and X here. For example, in case of fluorine, let us take this one here, and let us also consider this chlorine and this bromine. We can see the electronegativity of these atoms, fluorine, chlorine, bromine is decreasing. When it is decreasing, what would happen is the electrons stay almost midway between here and here. So, in this one electrons are more towards fluorine, and here it is less, and here it is less. That means, as electron density coming more and more towards the peripheral atoms, the angle start shrinking. Okay. On the other hand, if the electrons are coming more and more towards the central atom, angle will be increasing. So, with this analogy you can see that in this one, since the electron density is more directed towards the fluorine, so here not much electron density is there. So, the angle will shrink so that it can give more space for this oxygen double bond. On the other hand, here it is less electronegative, obviously you can expect angle to be little larger, and in this case angle can be even larger because little more electron density is going, or less electron density is coming towards the halide ions. So, you should be able to explain why this is happening in case of XPX. The trend can be explained. You can see here same example I have shown. So, essentially one can also analyze same thing in case of water and F2O. For example, if you want to look into the case of water and F2O, you should be able to tell which angle. For example, if I write something like this, you should be able to tell HOH and FOF, which angle is larger? This angle is larger and this is smaller, because here the electron density is something like this. So that since electron density drops towards fluorine atoms, okay, here angle shrinks so that it can give more space for these lone pairs to minimize interelectronic repulsion. So whereas here this angle will be little larger because electron density is residing more on oxygen atom. Okay. Okay. So that means now no matter what molecule is given, simply by looking into the electronegativity difference between the central atom and the peripheral atom, you should try to remember three structures I am writing here. One is like this, one is like this, and one is like this. So here if electron negativity of A is more electrons will stay here. As a result, angle shrinks, angle will shrink, small angle, and here electron density is coming here. So angle increases here, sorry. In this case larger angle, because lone pairs are at central atom, it increases. Okay, so last one. Okay. So in this case the electron density is moving away from A, so angle is small. So here it is intermediate. So just by looking into the electron negativity difference between the central atom and the peripheral atom, you should be able to remember these three. Once you remember these things, you can see what is the consequence of this one on the bond angle. In the first case bond angle will be normal, in the second case bond angle will be larger, in the third case bond angle will be smaller. So this is how you can use valence bond theory to almost understand the bond parameters such as bond distance and bond angle very clearly. So now I conclude valence bond theory. Of course, in my next class I will be telling you about the limitations we come across in valence bond theory, and I will proceed to the molecular orbital theory. So, have a pleasant reading